Good evening, Professor, and good evening, everyone. We are here to witness the sixth installment of the seminar organized by the Physics Department of the Sacred Heart College, Devra. I am Vasudev, and on behalf of my team, we welcome you all to the seminar presentation on the topic Decay Constant, Half-Life, and Mean Life. Special thanks to our mentor, Dr. Pius Augustine, for giving us this wonderful opportunity. We know that the Max batch and 5 groups of chemistry batch have completed the presentation beautifully. At this moment, I would like to congratulate each and every one of you who have completed the presentation, because you guys were really brilliant and your efforts are very much appreciated. As I said earlier, we have seen 5 presentations and we have surely reached a milestone, or checkpoint more precisely. So, I'll be briefing about what we have discussed so far. We had Group 1 in the presentation on the topic Classification and Properties of Atomic Nucleus, in which we discussed in detail about the general properties of neutron, classification of neutrons into slow neutrons and fast neutrons. Then we discussed in detail about the isotopes, isobars, isotones, isomers, mirror nuclei and isodiaphers. Please try to recollect the definition and examples. After that, the general properties of nucleus such as the atomic size, nuclear mass, the nuclear density and nuclear charge were discussed. You can see the equations of the same on the screen. We also had seen the binding energy and its graph. Then we had Group 2's presentation on the topic Basic Properties of Nucleus and Nuclear Forces, where we discussed in detail topics like charge, size, mass defect, density, spin, and binding energy, and the magnetic moment of the nucleus. Then we came across packing fraction, its significance, and how it is calculated were discussed. We also had a look at the 3 types of forces, and the most important point of discussion being the properties of nuclear forces. As you can see, nuclear forces are very strong, they are attractive in nature. They serve saturation property, that is, they are of short range. Nuclear forces are also charge independent and spin dependent. Furthermore, nuclear forces are found to interact between pairs of protons and pairs of neutrons. Also, these are non-central forces. Next, we witness Group 3's presentation, wherein we dive deep into the term radioactivity, starting from its historic significance to the common radioactive elements and the sources of radioactivity. A brief introduction to the 3 types of radioactive decay was included as well. Later, we discussed about the various sectors in which radioactivity finds its application, such as in the medical field as tracers and the treatment of cancer, in non-toxic food sterilization, in the field of agriculture, in nuclear power plant for the production of energy, and as nuclear weapons. Group 4's presentation dealt with the features of alpha, beta and gamma decay, and the table shows almost all the relevant features. Hope you remember all these points. Okay, alright. Moving on. Finally, we had Group 5 with Soddy-Fajan's displacement law and the law of radioactive decay. I assume that we are all thorough with the portions covered so far. With that being said, let's take a look at what we are going to learn today. This presentation is divided into 4 small portions, out of which Krishna will be dealing with decay constant, Mariya will be dealing with half-life, Anjala Franco will be dealing with mean life, and finally Rahul will be explaining about the activity of the radioactive substance. So, I hereby invite our group captain Krishna Suresh to continue with the presentation. Krishna, please.
Hi friends, today I am going to talk about decay constant. But before getting into the topic, let's have a look into the radioactivity. So, radioactivity. The word radioactivity is made up of 2 Latin words, namely radius, which means ray, and activist, which means activity. So, it's radiation activity. Thus, Radioactivity is the characteristic behavior of unstable cores of atoms spontaneously decaying to different nuclei and emitting radiation in the process. There are different types of atoms with unstable cores, and these are collectively referred to as radionuclides. You cannot tell when a nucleus will decay. But why do these nuclides decay at all? Because with stable nuclei, there is a certain stable proportion of protons and neutrons. But if there are too many or too few neutrons compared with the number of protons, this equilibrium in the core of the atom gets out of balance and the core becomes unstable decays. A nucleus needs no external influence to decay. A decay rate is a constant, and also for a given isotope there is a fixed probability of any single nucleus decays in unit time. So, decay constant or disintegration constant. What is decay constant? The definition of decay constant is the probability between the size of a population radioactive atoms and the rate at which the population decreases because of radioactive decay. So simply, the decay constant of a radioactive nuclide is its probability of decay per unit time. Suppose n is the size of population of radioactive atoms at a given time t and dn is the amount by which the population decreases in time dt, then by law of radioactive decay, the rate of change is given by the equation dn by dt is equal to minus lambda n, where lambda is the decay constant. The negative sign shows that n decreases as T increases. That is, number of radioactive atoms remaining without disintegration decreases with time. Integration of this equation yields n is equal to n0 e raised to minus lambda t, where n0 is the size of an initial population of radioactive atoms at time t is equal to 0. This is the equation for the radioactive decay law, and this shows that the population decays exponentially at the rate that depends on the decay constant. Another equation for decay constant is given by lambda is equal to 2.303 by t log n0 by n, where n0 is the initial number of nuclides, n is the final number of nuclides, and t is the time taken for decay. This equation is mainly used to solve figures. A problem related to this equation will be solved later on the session. So next point, the relation between the half-life T half and the decay constant lambda is given by the equation lambda is equal to ln2 by T half, or lambda is equal to 0.693 by T half. Decay law and decay constant. The rate of decay depends on the amount of substance present. Here's an example. Lambda being a fraction of atoms that decay is a very important concept. Here in our example we have 2 out of 8 apples decay, which is equal to 1 out of 4 apples decay and 3 out of 12 apples decay. And therefore we take lambda as 0.25 apples that are decaying per day. So with substituting in the equation dn by dt is equal to minus lambda n, we get the decay rate as 2 for sample 1, 1 for sample 2, and finally 3 for sample 3. Factors affecting decay constant. Radioactive decay is caused by the imbalances in the nuclear and electroweak forces inside the nucleus of atom. Therefore, temperature, concentration, etc. do not affect radioactivity at all. The number of atoms of radioactive element disintegrating in unit time at any instance is proportional to the number of atoms present. and it does not depend on the number of nuclei present or any external conditions. So, the decay constant of some isotopes are shown here. Here we will say that the decay constant is less than 1 in all these cases. However, for bismuth and lithium it is more than 1. This is so because the half-life of bismuth and lithium is very less than 1. So in 1 second, more than the whole of bismuth and lithium will decay. So here is a problem related to decay constant. So friends, this is the question, that is what we have, that is the half-life of fluorine 19 is 110 minutes. What fraction of sample decays in 20 minutes? Let's see how we can solve it. First of all, let us find out the data. So the data that is being given here is the half-life of fluorine, that is 110 minutes, and the time of decay, that is 20 minutes. So here basically we can say that we don't have the value of n0, either we don't have the value of n. So one thing, we can find out the ratio of n0 by n from the value of decay constant if we calculate it with the help of t-half. So let's start with writing the formula. The formula is lambda is equal to 0.693 t-half. Substituting the value of t-half, that is 110 minutes, we have got the answer as 6.3 into 10 raised to minus 3 minute inverse. So this is the value of decay constant. But this is not the final answer, that is what we need. We need the fraction that has been decayed. So let us find out another formula of the decay constant, that is lambda is equal to 2.303 by t log of n0 by n. By rearranging the equation, we have got a new equation as n0 by n is equal to anti-log of lambda t by 2.303. By substituting the values of lambda and t, the final answer we have got as 1.134. So from this we can estimate the amount which has been decayed. So for that we have to know what is the fraction which has been undecayed. So therefore the fraction which is undecayed, it will be n by n0, that is the reciprocal of 1 by 1.134. Taking out the reciprocal, we have got the value as 0.881. So for getting the amount of particles that has been decayed, we have to minus the answer from 1. So the final answer is 0.1119 fraction of this sample was decayed during the 20 minutes. So I hope you have understood this, and this is all about mine. I invite Mariya to continue the session.
Half-life. Half-life in radioactivity is the interval of the time required for one half of the radioactive sample to decay. In short, it is the measure of the time taken by a radioactive element to decay to half of its original amount. Half-life, the name itself shows what it signifies. SI unit is seconds of half-life. It is the characteristic property of various atomic nuclei and the particular way in which they decay. It determines how quickly it will decay. Since we are measuring the time taken by a radioactive element to decay to half of its original amount, it determines how quickly it will decay, and the half-lives can range from a fraction of a second to a billions of years. Here we are having two examples: uranium-238, which takes 4.5 into 10 raised to 9 years, and polonium-214, which takes 0.16 milliseconds. And the half-life of alpha decay ranges from about 1 millionth of a second, and for beta decay ranges upward from 100th of a second. Half-lives for gamma decay may be too short to measure. So therefore, alpha and beta decay are generally slower process than gamma decay. Next, we are having a graph, and the x-axis shows time e in multiples of half-life, and y shows the number of nuclides. And consider we are taking number of nuclides as 1000 when t equal to 0. and after completing one half-life, the number of nucleides is reduced to half of its initial amount. That is, it is reduced to 500. And after completing another half-life, the number of nucleides is again reduced to half of its initial amount. That is half of 500. That is 250, and it continues. Okay, now I have a question for everybody. Does half-life depend on the temperature? No, it does not depend on factors like temperature, concentration, etc. And each radioactive isotope will have its own unique half-life. Okay, and this does not depend on any such factors. Now we are having derivation, and as per the exponential decay law, nt equal to n0 e raised to minus gamma t. Nt is the number of nucleides in t seconds, n0 is the number of nucleides, initial number of nucleides. Lambda is a decay constant, and for half-life t is t half, and nt half is the half into initial number of nucleides. So n0 by 2 is n0 e raised to minus lambda t half. That is, we are substituting nt half equal to half into n0 values in the previous equation, and now we are dividing the whole equation by n0. So it becomes half into e raised to minus lambda t half. Now we are taking the logarithm, and it becomes negative log half equal to lambda t half, and keeping the t half there, and we are taking the lambda to the net side, so it becomes negative log half divided by lambda. And we have a law that is negative log 1 by x equal to log x. So we are substituting that, we are taking that in consideration, so it becomes log 2 by lambda. Log 2 is a constant, that is 0.693. So the t half is equal to 0.693 divided by lambda, and I hope that's clear. Next we have a question. The half-life of 71 zinc is 2.4 minutes. If one had 100 grams at the beginning of the decay, how many grams of 71 zinc would be left after 7.5 minutes has elapsed? Okay, so they has given the total time, that is 7.2 minutes, and the half-life, that is 2.4 minutes. And now we have to find the number of half-life, that is total time divided by half-life, that is 7.2 divided by 2.4, which is 3. So there are 3 number of half-lives, and the amount remaining after 3 half-lives, that is half raised to cube. That is, we know that after each half-life the amount is reduced into half of its initial amount, that is half raised to n, right? N is the number of half-lives, so here 3 is the half-life, so that gives 0.125. Therefore the amount of sample remaining after 3 half-life is 0.125 into 100 gram. 100 gram is already given, so it becomes 12.5 gram. So, okay, I hope that's clear. And now we are moving to the end of the session, and that is the applications of half-life. That is, one application is radiocarbon dating, the method for determining the age of an object containing organic material by using the property of radiocarbon. And the next application is for NTT. NTT is non-destructive testing, which is used by radiographers to make adjustment in the film exposure.
Thank you, Mariya. Hope you all can hear me. So, I'm going to do my presentation on mean life. Mean life and half-life of a process is a way to say how fast a process is occurring. And mean life, by definition, is the average lifetime of a radioactive nuclei, or it is the average time that the radioactive nuclei survives before it decays. As the name says, mean life, it is the mean of the lives of all the nuclei present in a sample. So, it can be written as mean life. Tau is equal to the total life of all the radioactive atoms in the sample divided by the total number of radioactive atoms in the sample. So, now as Mariya said, half-life is the time required for half the radioactive materials to decay, that is, to convert to another element, the daughter element. So for a sample of radioactive substance, if half of its atoms decayed in the first half-life, then we can expect there to be some kind of a well-defined average life expectancy. This is the mean life of the atoms, and this mean life is somewhat longer than the half-life of the element, that is, mean life turns out to be equal to the half-life divided by natural logarithm of 2. So we can write mean life tau is equal to the half-life t half divided by natural logarithm of 2, that is t half by 0.693, which is in turn equal to 1.44 t half. From this we can say that the mean life is 1.44 times longer than the half-life of that particular element. In this slide, you can see two graphs. These graphs represent the growth of daughter element and the decay of parent element. The graph 1 represents the decay of parent element and the graph 2 represents the growth of daughter element. And as we said before, the speed of any decay process can be described by the time it takes for the remaining amount to fall to half or a third or even any fraction at all. When we plot the amount of radioactive elements as a function of time, we find that it drops with an characteristic exponential decay curve, which helps us to show this half-life idea more mathematically. So here's a question. Suppose that the element did not decay exponentially, that is, with a half-life, but instead decayed linearly. That means the rate of decay was always equal to the initial rate. Like the first half in 1 minute and the second half in the next minute and then all gone sort of idea. So in such an idealized case, how long will it take to decay? Maybe 2 half-lives, right? So suppose we have 1000 atoms of radioactive element and initially there are 10 decaying per second. If it was to keep decaying at this rate, it won't, but imagine that it did. Then, how long would it take to completely vanish? The answer is, of course, 100 seconds, that is 1000 atoms decaying and 10 decaying per second. Then, with 100 seconds, all the atoms will decay. And now, this time, that is the time required for all the atoms to decay, or the time it took for all the atoms to decay, is precisely equal to the mean life of the real world element. So, if the atom behaved in a nice linear way that we will like to think in, then the time needed for them all to decay would be exactly equal to the mean life of the element. But we can see that the curve is exponential, or the number e is tied into the simple idea of linearity. This same idea applies to the growth of the daughter element. Suppose for simplicity, that is, the daughter element is not itself radioactive. Initially, there are no daughter atoms at all, and gradually they grow as the parent element decays. Their growth must eventually flatten out, and this takes infinite time. For the same reason that the parent element takes infinite time to fully decay. So if the growth of the daughter element continue at the initial rate, which doesn't really, it would take a mean lifetime to be fully composed of the daughter element, for the sample to be fully composed of the daughter element. So the idea I intend to give through these two graphs is that the mean life is the time that the radioactive sample will take to completely be composed of the daughter elements or to completely decay if the sample behaved in a linear way or continued to decay at the initial rate. So that's all about mean life. Hope you all understood. So now let us move on to the derivation of the relationship between mean life tau and the decay constant lambda. So let n0 be the initial number of atoms at a time t is equal to 0 and dn the number of atoms that decayed in a time t and n be the number of atoms that are left undecayed after a time t. From this, we can say that the total life of dn number of atoms is t multiplied to dn and total life of n0 atoms will be integral 0 to infinity t multiplied to dn. And now consider the radioactive decay law, that is n is equal to n0 e raised to minus lambda t. On differentiating that, d by dt of n is equal to minus lambda into n0 e raised to minus lambda t. On taking dt to the other side, we get dn is equal to minus lambda into n0 e raised to minus lambda t dt. So, as we said before, mean life is given by tau is equal to the sum of life of all the radioactive atoms in the sample divided by the total number of radioactive atoms present in the sample. So we know that the total number of atoms, that is the initial number of atoms, is n0 and the total life of n0 atoms is integral 0 to infinity t into dn. And now substituting the values of tau, we get tau is equal to integral 0 to infinity t dn, that is substituting dn, we get tau is equal to integral 0 to infinity t into lambda n0 e raised to minus lambda t dt divided by the total number of atoms, that is n0. And now cancelling out n0, we get tau is equal to lambda into integral 0 to infinity t into e raised to minus lambda t dt. On integrating this, we get tau is equal to lambda into 1 by lambda square, which equals 1 by lambda. From this, we can conclude that the mean life tau equals to the reciprocal of decay constant. So, we know that mean life tau is the reciprocal of decay constant lambda. Now, let us try to write the radioactive decay laws in terms of mean life. So, the two radioactive laws are n is equal to n0 e raised to minus lambda t and r is equal to r0 e raised to minus lambda t. R is the radioactivity. And substituting lambda is equal to 1 by the mean life tau, we get n is equal to n0 e raised to minus t by tau and r is equal to r0 e raised to minus t by tau. Hope you all understood. That's all about my topic. So now I invite Rahul to continue with the presentation. Thank you.
Hi, I am dealing with the topic activity of a radioactive substance. So what is activity? Activity we can represent it as R. In radioactive process, activity is the number of disintegrations per second, or in other words, it is the rate of decay in a radioactive decay process. I repeat, it is the rate of decay in a radioactive decay process. We all know rate means it is with respect to time. Then the equation for activity is equal to delta n by delta t, or R is equal to delta n by delta t, where delta n is the change in number of undecayed nuclei. More clearly saying, from the initial state, the number of disintegrations occurred to undecayed nuclei in that radioactive decay is delta n, and delta t is the change in time in seconds. So SI unit of activity is becquerel BQ, and 1 BQ is equal to 1 decay per second. Henry Becquerel was the first to discover radioactivity. So activity has its unit becquerel in respect with him. Other practical units are curie and Rutherford, where 1 curie is equal to 3.7 into 10 raised to 10 becquerel and 1 Rutherford is equal to 10 raised to 6 becquerel. Now in this slide we deal with activity at an instant. It could also be referred as a relation between decay constant and activity. It says activity is equal to decay constant multiplied by number of undecayed nuclei. So activity we know it is delta n by delta t, that is equal to minus lambda n, where lambda is the decay constant and n is the number of undecayed nuclei. Since radioactive decay is a decreasing process, then it is income. So R is equal to lambda n. Hence we know R is equal to delta n by delta t, where R is activity in becquerel, lambda is the decay constant and n is the number of undecayed nuclei. Hope you remember the equation of radioactive decay law, that is Nt is equal to N0 e raised to minus lambda t. This was the equation for the number of undecayed nuclei at an instant. By integrating the equation R is equal to lambda n, we get a similar equation, that is RT is equal to R0 e raised to minus lambda t, where RT is activity at that instant or final activity, R0 is the initial activity, lambda is the decay constant and t is the time. So I repeat the equation, RT is equal to R0 e raised to minus lambda t. Now let's discuss a problem. A sample of carbon-14 whose half-life is 5730 years has a decay life of 14 disintegrations per minute per gram. A fossil is found to have radioactivity of 4 disintegrations per minute per gram of its present carbon. So how old is the new fossil? Let's discuss on the data given. Given half-life T half is equal to 5730 years of carbon-14 and it has decay life of 14 disintegrations per minute per gram. It is also given present carbon has a decay life of 4 disintegrations per minute per gram. So the activity of present carbon or at this instant is given. So RT is equal to 4 disintegrations per minute per gram. And R0 is equal to 14 disintegrations per minute per gram. Hence it is the activity of carbon-14. So we know the equation RT is equal to R0 e raised to minus lambda t. So substituting in the values, 4 is equal to 14 e raised to minus lambda t. 4 by 14 is equal to e raised to minus lambda t. Taking natural log on both sides, which give minus lambda t is equal to ln 4 by 14. So lambda t is equal to ln 14 by 4, that we highlight as first equation. In the question, it is asked how old is the fossil. So T is the term to be found out and lambda is the decay constant. We had an equation connecting half-life and decay constant, that is T half is equal to 0.693 by lambda. Hence T half is given. We can use this equation to proceed. So multiplying and dividing the right hand side of the equation by T. So T half is equal to 0.693 by lambda into T by T. Rearranging the equation gives T is equal to T half into lambda T by 0.693. We know lambda T is equal to ln 14 by 4, which we highlighted as the first equation, and T half is given as 5730 years. So substituting in the values, T is equal to 5730 by 0.693 into ln 14 by 4. So by calculation we get T is equal to 10,358 years, which means this much year old is the fossil. So hope it is clear. So that's all with our session. Let's go for a recap on today's topic. First we discussed decay constant, its equations, decay constant of some elements and factors affecting decay constant. Then we discussed half-life, graph related to half-life, equations and applications of half-life. Then we discuss mean life, graphs related to mean life, and as well as the equations. At last, we discuss activity and its equations and problems from each of the subtopics. So that's all with our session.
With that, we conclude our presentation. We assume that the presentation was comprehensible and all of you have got at least some idea about the topic. I thank each and every one of you for your cooperation and especially the batch we have collaborated with. Once again, Thank you, Professor, for giving us this platform. Our sincere gratitude. Thank you.